The second presentation in this session will be dual agent deep reinforcement learning for deformable face tracking. This is joint work by Minghao Guo, Jiwen Zhou from Tsinghua University.
Hello everyone. My name is Minghao Guo. I'm from the Department of Automation, Tsinghua University. My topic today is the dual agent deep reinforcement learning for deformable face tracking. This is a joint work both with Professor Jiwen and Zhou. I will give a brief review of the deformable face tracking problem and some classical methods, and I will tell you about how we address this problem in a dual agent manner. So let's get started. The problem of deformable face tracking is to recover a set of accurate fiducial points in conjunction with successfully tracking the face across the long-term sequences. It has a crucial role in numerous applications as it can output signals of higher-level methodologies to compute motion dynamics and deformations. Here is a video example from the dataset of 3D Mempo Deformable Face Tracking Challenge in SSV Workshop 2017. The problem of deformable face tracking basically involves two categories of approaches, the detection and the tracking. Here we refer to the detection as the landmark detection and the tracking as the bounding box tracking. So there are following ways of combinations of these two basic approaches. For the pure detection, which means detect the landmarks per frame, that equals to the image-based face alignment. For the pure tracking, this refers to the landmark tracking methods. And for first tracking, then detection, this refers to the tracking by detection methods. And there remains the first detection, then tracking methods. Here, let's review the landmark tracking, tracking by detection, and first detection, then tracking methods in detail. For landmark tracking, typical methods including the incremental learning methods proposed in CPR 2014, and the encoder-decoder framework proposed in ESSV 2016. For these methods, the landmark positions of each frame are adjusted incrementally. The tracked landmarks of previous frame is utilized as the initialization. Because changes in facial pose and expression from one frame to the next one are typically small, the initialization is much closer to the correct solution. This makes these methods could partially handle the large variation of pose and expression over the whole video. However, errors in the tracked landmarks can accumulate over time, which in turn results in polar and polar initialization and eventually make the tracker lose tracking and the drifting arises. This phenomenon is much more easier to see in the cases of dense landmarks, such as the 49 or 68 landmarks, which was broadly used. For tracking by detection methods, there exists a complementary survey proposed in IGCV 2016. These methods first generate a high-scored bounding box covering the face region, and then apply face alignment to localize facial landmarks based on the bounding box. The tracking by detection methods could eliminate drifting to some extent, for the landmark detection procedure is independent between frames. However, in the tracking by detection methods, models are trained individually and utilized in a serial manner. Hence, the accuracy of the alignment depends heavily on the generated bounding box. Here is an example of the field cases for tracking by detection methods. As we can see, a small bias of the bounding box from the ground truth could result in a very poor fitting of the landmarks. For first detection, then tracking, it is widely used in human pose tracking problems for multiple person cases. The key points of each frame are first detected, and then the detected points are linked by matching algorithms over time to perform tracking. This strategy is a promising method to deal with deformable face tracking for multiple face cases. So how about joint detection and tracking? We want to use the bounding box tracking to eliminate drifting issue which arises in landmark tracking methods. We'll find a way to explicitly utilize the interaction of the two models to avoid the heavy dependence risk in tracking by detection methods. This is the motivation of our dual agent deep reinforcement learning. In our proposed method, we formulated the deformable face tracking problem as the estimation of the joint probability of bounding box and the landmarks. For the kth frame in the face video, we have the image IK of the current frame, the tracked bounding box of previous frame BK-1, and the landmarks of previous frame VK-1. We aimed to output the bounding box BK and the landmarks VK for the current frame. That is the output joint probability under the condition of the inputs. Following the Bayesian theory, the joint probability could be derived as follows in two equivalent ways. Let's focus the last equation of the two expressions. This is so-called the probabilistic duality. It is important to hold this probabilistic duality during the training of the two models, not only because it is an essential condition for the optimality of the dual models, but also it is an explicit way to formulate and further utilize the intrinsic connection of the dual models. To hold this probabilistic duality, we consider the two models as dual agents, the bounding box generation as the tracking agent, and the landmark detection as the alignment agent. These two agents output the marginal distribution in the equation. For the conditional distributions, which are also regarded as the connections of these two tasks, we introduce communicating messages between dual agents as alternatives of the two conditional distributions. Here we compare our DADR learning scheme with other methods. The tracking by detection methods and the first detection then tracking methods focus on single task learning, which has no guarantee to hold the probabilistic duality. For multitask learning, it aims to directly output the joint probability, which has an assumption that these two tasks share the same input space and a coherent feature representation. It is usually too strong in practical application. Our DADR disentangles the connection of two tasks and explicitly exploits the synergy between them. So how to train the dual agents and the communicating messages? As we can see, there are 4 unknown terms to optimize. Inspired by the recent success of reinforcement learning, we propose a deep reinforcement learning framework. This training scheme can avoid designing a complex loss function which is needed in the supervised learning, since our models can get feedback by the reward. Also, the dual agents along with the messages are also trained simultaneously, which could explicitly satisfy the probabilistic duality. The learning of them is facilitated by using the deep Q-learning algorithm. The basic pipeline is as follows. For each frame in the video, firstly, the state is initialized by the terminal state of the previous frame. Then, based on the observed state and the received messages, these two agents decide a sequence of actions to adjust the target's bounding box and regress the facial landmarks simultaneously. The agents go to the next frame until the detected landmarks are finalized. The network of the tracking agent is a VGGM model. The output of the FC5 layer is concatenated with the message received from the alignment agent. And the final FC6 layer predicts the Q values of the 6 movements of the bounding box. The network of the alignment agent is designed based on the static hourglass network. The predicted map is fed to a confidence network to output the Q value of the stop or continue action of the alignment agent. The communicated message is a deconvolutional layer and the RSTM unit respectively. For the message passed from the tracking agent to the alignment agent, we aim to provide prior additional textual information. As the tracking agent is sensitive to the textual features of facial parts, while the alignment is difficult to judge the facial or non-facial parts, the message is a promising way to provide conditional information to enhance the robustness of the alignment agent for the occlusion cases. We select the output feature of the Conv2 layer in the tracking agent and concatenate it in depth access with the feature map in the hourglass network. We adopt a deconvolution layer to match the size of the feature map. The message passed from the alignment agent to the tracking agent provides 3D pose information for bounding box tracking. As the human head has a limited range of the rotated angle, the pose variation could help the tracking agent to better track the face. For example, if the head of a certain frame turns to the extreme left, then the head had to turn right or hold on in the following sequences, where the tracking agent should perform corresponding actions. We take the normalized coordinates of the predicted landmarks as a representation of the 3D pose information and adopt RSTM to memorize the pose variation through the time series. Thus, the tracking agent could adjust the bounding box position according to the facial pose variation. As for the definitions of the Markov decision process, the state is defined as the current image region extracted by the bounding box. And the actions are totally 8 types for 2 agents, including 6 movement actions and stop or continue action. The reward for the tracking agent is the landmark detection accuracy improvements, and for the alignment agent is the finalized landmark accuracy. We evaluated the performance of the proposed DADR on the 300 VDAP category 3 dataset. This dataset contains 14 videos with more than 20,000 frames. The videos are captured in totally arbitrary conditions, including serial occlusions and extreme emulations, which is a very challenging data set. The experiment results from both the 49 inner points and 68 points are illustrated at the figures. As we can see, our DADR achieves the state-of-the-art over other methods. We also performed two analyses, the tracking analysis and the alignment analysis, to illustrate how communicating messages in the dual-agent training manner works. The baselines are the agents without message communication. As the results show, the community message play an important role for improving the robustness of both bounding box tracking and the face alignment, especially for the heavy occlusion and large pulse cases. Here is a demo of our DADR compared to several other methods. As we can see, our DADR is more robust to extreme conditions and is both more accurate and more stable. So here are some other experimental examples. So to conclude, we propose a deformable face tracking method which perform bounding box tracking and landmark detection simultaneously in a dual-agent manner. And we introduce deep reinforcement learning to train the agents to hold the probabilistic duality. Experiment shows our DADR is robust to the extreme conditions, including heavy occlusion and large pulses. And I have almost done my presentation today. Thank you very much.
So are there any questions?
The first question is that, are you doing any warm-up or pre-training for your agents?
Yeah. We use the pre-trained models for the two agents, but not for the messages.
Okay, and have you compared your reinforcement settings to the fully supervised training?
Yeah. As I have quoted in the presentation, there is a paper which called dual supervised learning, and it trained the probabilistic duality with a regularization loss function, and it has empirical distributions to estimate the two terms in the equation. And we tried this training scheme, and it does not work quite well. Maybe it's because that paper, the method is worked on the translation, such as the Chinese to the English and the English to the Chinese. It is very directly duality to hold the duality. But the tracking and the alignment, it does not have this property.
Okay, thank you.
Any other questions? We have time for one question. If not, let me ask you one question. Also like a follow-up question. So you use two agents, and the second agent just tell you stop or continue, right? And my question is like, what would actually happen if the second agent would be just stupid, just continue in the first agent? So is it really necessary to have two decisions at the two steps, or could you also have like a single agent?
So you mean we train the agent at the same numbers of iterations?
Yeah.
And this way it means that it is very similar to the it's very similar to the cascade regression methods. And as we can see, for the video cases, the some frames is very difficult, and it needs to have the more iterations to adjust the bounding box and the alignments results. But for some frames, it is very easy, so it's just one iteration or two iterations, it is okay. But the cascade method, it does not work.
Okay. Yeah, thanks to speaker again.